We want to talk about when can we construct a regular n-gon. So before we can do this, let us fix some notation. So let us put z by mz, the cyclic group of order m, as cm. So recall that u of p to the power of a, this is a cyclic group of order p a minus 1, p minus 1, if p is odd, and if p is even and a is greater than 2, then it is cyclic group of order 2 times cyclic group of order 2 to the power of a minus 2. In case a is precisely 2, then this 2 minus 2 becomes 0, so 2 to the power of 0 just gives you 1, so this becomes cyclic group 2. So p to the power of a is 2 to the power of 2, so a is 2. So this is an important result which is covered in elementary lectures on group theory, so this one needs to keep in mind, very important fact. So say if n is given like this, 2 to the power of k, and then there are distinct primes p1 to pr, then you know that u of n is u of 2k u of p1 times this. So this result we also know from group theory. Now if this is true, then this order of u of n, so this order of u of n, now use this formula. So if it is 2 to the power of k, it will be for this you will be 2 to the power of something, so 2 to the power of say some beta. For p1, all these other primes are distinct and odd because all the even primes are here and all these are odd primes, and all of them have power just 1, so this term becomes 1, so p to the power of 0, this becomes 1, so they just have p minus 1 order. So order here is for up1 is p minus 1, up2 is p minus 2, upr is pr minus 1. Now recall the definition of a Fermat prime. So Fermat prime looks like this: pi is 2 to the power of say kappa I plus 1. So pi minus 1 will be 2 to the power of 2 to the power of kappa I. So if each of these is a Fermat prime, so if this p1, p2 all the way to pr are Fermat prime, then all these p1 minus 1 will be a power of 2, pr minus 1 will be power of 2. So you plug in these values in place of this and you get order of u of n, which is precisely the number of integers relatively prime to n which are greater than 1 and less than n. This will be precisely this. Yeah, so instead of p1 minus 1 we have 2 to the power of kappa 1, and till r we have 2 to the power of this 2 to the power of kappa r. So we have done this. So if n is of this form where pi is a Fermat prime, then result in this direction holds. We want to prove that if phi of n, this Euler's phi, is 2 to the power of some eta, then this also implies that n is of this form. Now this will require a little bit more effort, but we will just put a remark which will basically make things clear. So because for this n you have to first decompose it into its prime factors, and then if it is 2 to the power of eta, we have no choice but to have certain primes of this form. So this should be clear from the remark. So the remark is, so say you have a prime which is 2 to the power of c plus 1. So we are saying these primes of this form can only be prime if c is a power of 2. So c is a power of 2. So that is, this p can only be prime if it is of this form. That is 2 to the power of 2 to the power of something. Now if it is c is not 2 to the power of something, so if c is not say 2 to the power of some factor, say gamma, then c has an odd factor, say t, and this will give a factorization, and if it gives a factorization then you no longer have a prime. So for example, zt plus 1 for t odd, factors like this: z plus 1 times zt minus 1 minus zt minus 2, this plus 1. Now instead of this you put 2 to the power of st plus 1. So instead of z, now we have 2 to the power of s. So wherever there is z, you put 2 to the power of s. This. So if this is equal to some prime, if you say it is equal to some prime, you have a factorization right here. Now instead of z, we are putting 2 to the power of s. So So this is our z. So you have factorization, so this is no longer prime. So therefore, this works in this direction also. There's a bit more to write down, but essentially this is the argument. Now the idea is this, that we want to use this result to construct an n-gon. And before we go further, another remark is that Fermat primes are not all prime numbers. For example, 2 to the power of 32, which is 2 to the power of 5 plus 1, this is not a prime number. Some of them are prime, some of them are not prime. But the essential point is that if you have these Fermat primes like this, n is 2 to the power of kp1 pr and pi is a Fermat prime, then var phi of n is 2 to the power of n. So corresponding to this irreducible and separable cyclotomic polynomial, we had a Galois extension. So this we have shown. So Galois extension, so this Galois group is equal to degree of extension, which is equal to var phi of n. This we have shown before in the lecture on irreducibility of cyclotomic polynomials, and this is equal to, this is just the definition. By definition, var phi of n is the order of this group u of n. That is number of elements relatively prime to n, which lie between 1 and n, and 1 including. So this we already know. Now let us come to the definition of constructible numbers. So recall that this alpha is constructible. Then this, you adjoin alpha to rationals over rationals. This is 2 to the power of some number nu. So if you want to construct an n-gon, so the first thing is you have to first construct the real coordinate of zeta n. So we are after all trying to take a circle and trying to make the first cut. You start from here, which is 1, you put your compass here, you want to make the first cut here. But to make the first cut, you first know what is the real coordinate of this. So real coordinate of this is this part, cosine 2 pi by n. So zeta n is exponential 2 pi, this I is complex over n, and the real part of this is cosine 2 pi by n, which comes from zeta plus zeta conjugate divided by 2. Notice that zeta conjugate is precisely equal to zeta minus 1. So now notice that you adjoin, so instead of zeta n, I'm going to just write zeta. So this is our first primitive root, nth root. So for n-gon, you have to construct first is this primitive root. So this we are denoting as zeta. So first notice that if you adjoin this primitive root of unity, nth root of unity, to rationals, and this degree of extension over rationals, you adjoin cosine 2 pi by n to it, this is 2. Now this comes from this polynomial x square minus 2 cos 2 pi n x plus 1. So this lies over this field, adjoin x to it. So this cos 2 pi n is right here. Now the root of this polynomial is precisely zeta. So this is easy to see. So you plug in zeta here, you get zeta square minus 2. So cosine 2 pi by n is nothing but zeta plus zeta conjugate divided by 2. So zeta plus zeta conjugate divided by 2, and we are saying instead of x, plug in zeta plus 1. So now you can see that this cancels out, and this is equal to zeta square minus, you have zeta square plus zeta conjugate minus here, and then plus 1. So this cancel out, this will give you minus 1 plus 1, this is 0. So zeta is the root of it. Now so this degree of extension is at most 2, and we are saying it is precisely 2 because zeta does not lie in this field, adjoining cosine of 2 pi by n to rationals, because zeta is a complex number, and if you adjoin cosine 2 pi by n to rationals, this will be a subset of real numbers, and zeta will not lie in real numbers. So zeta does not lie in our given field, so this degree of extension is 2. So now we already know that this degree of extension here is Euler phi of n. So this is Euler phi of n. So this we will rewrite in two parts, first part and second part. Notice that these two terms are the same, so they will cancel out to give you this. This is var phi of n. So this first term is 2, This comes from right here. This you copy right here. So therefore this second term has to be equal to var phi of n, or phi of n, divided by 2. Now for this to be constructible, so we want this to be constructible. So this is our alpha. So alpha is constructible. Q alpha over q is this 2 to the power of nu. So we want this to be the power of 2. So therefore, this side is getting divided by n. So we want var phi of n to be a power of 2, and which is satisfied precisely by this n equals to this 2 to the power of k p1 to all the way to pr, where pi is a Fermat prime. So we have constructible if our real part is constructible. So if our polygon is constructible, then we obviously have this phi of n is of such a form. This implies that our phi of n is of such a form, which is a power of 2. So now again we have just proven that constructible implies that var phi of n is 2 to some power, that is of this form, which implies that n is like this, where p of I is a Fermat prime. So this much we have proved. Now we want to prove the other direction, and then we will have n-gon is constructible if and only if this Euler phi function is of the form 2 to the power of eta, that is if and only if n is of this form 2 to the power of k p1 times p2 times all the way to pr, where pi is a Fermat prime. So let us now go in the opposite direction. So recall that element alpha is constructible if and only if f is of the form this alpha adjoint to rationals, and this can be obtained by a series of quadratic extensions. So you start with f0, then f1, all the way to this f theta, which is alpha adjoint to rationals. So all these extensions are of degree 2. So each of these extensions is of degree 2. Obviously it cannot be degree 1, because then they are the same fields. So there is no extension like this. So you have this quadratic extension here. Only then our number is constructible. So now say if your this phi of n is 2 to the power of lambda, it is some power of 2, which is obviously now the order of our Galois group, and this would imply that our this sub extension of it, or subgroup of this, will also be power of 2. So this is also cyclic group of power 2. So since this is cyclic group of power 2, it also has series of subgroups. So for example, if you have a group of order 8, it will have subgroup of order 4, which will have subgroup of order 2. So you have these subgroups. Similarly here you have these subgroups. So this subgroup has our order 2 theta, and then the second one will be 2 theta minus 1, just like here, all the way. So this will have 2 to the power of 0, which is 1, just like this. And then you have quadratic extensions, obviously, of 2, as you can see. So the Galois correspondence here will carry this to these fields. So if your var phi of n is 2 to the power of lambda, then this part which we need to construct, this is cosine 2 pi by n, will also have a cyclic group of order 2 to some power, which will give us a series like this, which by Galois correspondence will be in 1-to-1 correspondence with this. Therefore you will get this extension of degree 2, and therefore your element will be constructible. So we have gone from here to constructible element. So n-gon is constructible if and only if this var phi of n is 2 to the power of eta. So this is what we have proven. But this is so if and only if this, so you have an eta here, if and only if this n is of this form, 2 to the power of k p1 p2 all the way to some pr, where each of these pi's are Fermat primes.